Champions, chase your dreams so bright. Let's learn global perfect training.
Have you ever wondered how computers keep track of everything? From your favorite video game characters to all the items in a giant online store, it all comes down to data. But data isn't just a jumbled mess. It's organized in a very specific way, like building blocks stacked one on top of the other. The smallest block is called a field. A field is just one single piece of information. Think about a label on a jar. The label for product name is a field. The label for price is another field. Each one holds just one type of data. It's the simplest, most fundamental unit of information we work with. Now, what happens when you take a bunch of these fields and put them together? You get a record. A record is a complete set of fields that all describe one single thing. Imagine you're looking at one specific item in a store's inventory, like a cool science kit. The record for that kit would include the product name field, for example, volcano making kit, the price field, like $19.99, and the quantity in stock field, such as 50. All those pieces of information together form one complete record for that one item. It's like a single row in a spreadsheet, telling you everything you need to know about that one specific science kit. So we have fields and we have records. What's next? When you group a bunch of related records together, you create a file, which in the database world, we often call a table. If you took the record for the volcano making kit and added the records for the DIY rocket, the microscope set, and every other toy in the science store, you would have a complete inventory file, or an inventory table. It's a collection of all the records that are of the same type. Think of it as the entire spreadsheet, with many rows, which are records, and many columns, which are fields, all organized neatly. This table holds all the information about every product the store sells. Finally, we get to the biggest building block, the database. A database is a collection of related files or tables. The science store's database wouldn't just have the inventory table. It would also have a customers table with customer names and addresses, and an orders table with information about who bought what. All these tables are related and stored together to run the entire store. So, the order is crucial. Fields make up records. Records make up tables, and related tables make up a database. Getting this order wrong is a common mistake. A field is not a database, and a database is not just one big file. It's an organized collection of them. It's more than just a big file. So what makes a database so special? A database is a shared, integrated computer structure that stores a collection of related data. The key words here are shared and related. We don't just throw random files together. The customers table and the orders table belong in the same database because they are connected. A customer places an order. By keeping them together, the computer can easily look up a customer's information when they make a purchase, or find all the orders placed by a single customer. This grouping makes the data powerful and useful, allowing a business to see the big picture instead of just isolated facts. Most modern databases are relational databases. This sounds complicated, but the idea is simple. It means the data is stored in tables, and the relationships between those tables are also stored and managed. Let's think about a company that makes bicycles. They might have a suppliers table with information about who sells them parts, like tires and chains. They would also have a parts table listing all the individual parts they use. A relational database allows them to link these tables. They can connect the super tire Komatsu supplier record to the 26-inch mountain bike tire part record. This way, when they need more tires, they know exactly who to call. It's also important to understand what a database is not. You might hear terms like data warehouse, data lake, or data mart. These are different. A database, often called an operational database, is built for the day-to-day running of a business, processing orders, updating inventory, managing customers. A data warehouse, on the other hand, is designed for analysis and reporting. It pulls data from many operational databases to find long-term trends. A data lake is even bigger, storing vast amounts of raw, unstructured data for later analysis. And a data mart is a smaller, focused version of a data warehouse for a specific department, like sales. A common misconception is to use these terms interchangeably, but they serve very different purposes. The power of a relational database comes from this structure. By organizing data into separate related tables, we avoid a lot of problems. For instance, we don't have to type out a supplier's full address every single time we list a part they provide. We just link to their record in the supplier's table. This saves space, and more importantly, it prevents errors. If the supplier moves, we only have to update their address in one place, not in hundreds or thousands of different part records. This principle of reducing repetition is a cornerstone of good database design and makes information much easier to manage. Now, having a bunch of organized tables is great, but how do we actually use them? How do we keep the data safe and make sure everything runs smoothly? That's where the Database Management System, or DBMS, comes in. The DBMS is a special software program that acts like a butler for your database. It stands between the users, that's you, and the actual database files stored on the computer. You don't touch the data directly. You make a request to the DBMS, and the DBMS handles it for you. It's the gatekeeper, the organizer, and the helper all rolled into one. One of the most important jobs of the DBMS is to manage how data is stored and to keep it safe. It controls access, making sure only authorized people can see or change information. Think about a bank's database. You should only be able to see your own account balance, not everyone else's. The DBMS enforces these security rules. It also helps with data integrity, which means making sure the data is accurate and consistent. For example, it can make sure that the price field for a product can only contain numbers, not letters, preventing silly typos from causing big problems down the line. A huge benefit of a DBMS is that it allows many different people and programs to use the same data at the same time. This is called concurrency control. Imagine a concert ticket website. Thousands of people might be trying to buy tickets for the same show simultaneously. The DBMS manages this chaos, ensuring that two people don't buy the exact same seat at the exact same moment. It locks a record while one person is using it, and then unlocks it when they are done, all in the blink of an eye. Without a DBMS, this would be a complete mess of double-booked seats and angry customers. Let's consider a real-world example. A company has a central database with all its customer information. The sales team uses this data to contact clients and record new sales. At the same time, the accounting department uses the very same data to send out invoices and track payments. They aren't using separate copies. They are both accessing the single, shared database through the DBMS. When a salesperson updates a customer's address, the accounting department instantly sees the new address. The DBMS provides this one unified view of the data, ensuring everyone is working with the most up-to-date information. So many things. A database management system has a whole toolkit of functions that make it incredibly useful. We can group these functions into 4 main jobs: data development, data maintenance, application development, and data interrogation. That sounds like a lot, but let's break it down. It's all about creating the database, keeping it healthy, building things with it, and asking it questions. Each function is essential for a database to work properly and be useful to an organization. Let's start with building the house before we move in. First up is data development. This is where you design the structure of the database. Before you can put any data in, you have to define what the database will look like. This is done by creating a schema, which is like a blueprint for the entire database. The schema defines all the tables, the fields within those tables, and the relationships between them. For example, during development, you would decide to create a customer's table. You would then define its fields: customer ID, first name, last name, and email. You'd also specify data types, like making customer ID a number and first name text. Once the database is built, it needs to be cared for. This is data maintenance. Data is not static. It changes all the time. New customers sign up, people move to new houses, and products go out of stock. Maintenance involves the 3 fundamental operations: adding new data, modifying existing data, and deleting old data. For instance, when a new customer, Jane Doe, creates an account, a new record is added to the customer's table. If she later changes her email address, her record is modified. If she closes her account years later, her record might be deleted or archived. The third major function is supporting application development. A database isn't very useful if people can't interact with it easily. The DBMS provides tools for programmers to build applications that connect to the database. These applications can be anything from a public website for shopping to an internal report-generating tool. For example, a developer could build a monthly sales report application. This program would ask the DBMS to pull all the sales data for the past month, organize it by product, and present it in a clean, easy-to-read format for managers. These applications are the friendly faces of the database. Finally, we have data interrogation. This is a fancy way of saying asking the data questions. The DBMS provides a language, usually SQL, that allows users to search, filter, sort, and retrieve data in countless ways. This is often done through queries. A manager might ask an ad hoc or on-the-spot question like, "Show me all customers from California who purchased a DIY rocket in the last 6 months." The user doesn't need a pre-built report. They can just write a query to get the exact answer they need right now. This powerful questioning ability is what turns raw data into valuable business intelligence. For a database to work its magic, it needs a reliable way to tell records apart. Imagine a phone book with 3 people named John Smith. How would you know which one is your friend? Databases solve this problem with something called a primary key. A primary key is a field, or sometimes a set of fields, that contains a unique value for every single record in a table. No 2 records in the same table can ever have the same primary key value. This unique identifier acts kind of like a social security number or a fingerprint for each record, making sure we can always find the exact one we're looking for. Think about a student's table at a school. Using a student's name as a primary key would be a bad idea, because you could easily have 2 students named Maria Garcia. Instead, schools assign each student a unique student ID number. This student ID is the perfect primary key. It's guaranteed to be unique, and it will never change. Similarly, a company might use a vendor number to uniquely identify each of its suppliers, or a product SKU to identify each item in its inventory. A common mistake is choosing a primary key that isn't truly unique, which can lead to chaos and data corruption. Now, if primary keys help us identify records within one table, how do we link different tables together? That's the job of the foreign key. A foreign key is a field in one table that is the primary key in another table. It's the key that unlocks the door to a foreign table, creating a logical link or relationship between them. This is the fundamental concept that makes relational databases relational. It's how we connect customers to their orders, and orders to the products they contain. Without foreign keys, our tables would just be isolated islands of information. Let's look at an example. We have a suppliers table where supplier ID is the primary key. We also have a products table that lists all the products we sell. In the products table, we can add a field called supplier ID. This supplier ID field in the products table is a foreign key. It refers back to the supplier ID primary key in the suppliers table. If a product record has a supplier ID of 502, we can follow that link back to the suppliers table to find out everything about supplier number 502, their name, address, and phone number. A common error is a dangling foreign key, where a foreign key value, like supplier ID 502, exists in the products table, but no matching supplier exists in the suppliers table. A good DBMS helps prevent this. Before we even start building a database, we need a plan, a blueprint. In the world of databases, that blueprint is an entity relationship model, or ERM. An ERM is a diagram that shows us the main things our database will store and how they connect to each other. The things are called entities, which usually become the tables in our database, like customer, product, and order. The connections are called relationships, which show how the entities interact. Drawing this out first helps us think clearly about our data and, honestly, helps us avoid major design flaws later on. The relationships in an ERM have a special property called cardinality, which describes the number of instances of one entity that can be associated with instances of another entity. There are 3 main types of cardinality. The first is a one-to-one relationship. This is pretty rare, but it means one record in a table is linked to exactly one record in another table. For example, in a company database, each employee might have exactly one company car, and each company car is assigned to only one employee. It's a direct, exclusive pairing. A much more common and useful relationship is one-to-many. This is really the workhorse of database design. It means that one record in a table can be linked to many records in another table, but not the other way around. Think about our customer and order entities. One customer can place many orders over time, but each individual order belongs to only one customer. This is a classic one-to-many relationship. The one side is the customer, and the many side is the order. This structure allows us to see a customer's entire order history easily. The third type is the many-to-many relationship. This happens when many records in one table can be linked to many records in another. Consider orders and products. A single order can contain many different products, and at the same time, a single product, like a popular science kit, can appear on many different orders. This is a many-to-many relationship. In a relational database, we can't implement these directly. We handle them by creating a third table, often called a linking or junction table, like order details, that breaks the many-to-many relationship down into two one-to-many relationships. All three cardinality types are important for accurately modeling the real world. So, we have this beautifully designed database, managed by a powerful DBMS. How do we actually communicate with it? How do we ask it our questions or tell it to update information? We use a special language called SQL, which stands for Structured Query Language. SQL is the universal standard language for interacting with relational databases. Whether you're using a database from Oracle, Microsoft, or some open-source project, you'll be using some form of SQL to talk to it. It's really the bridge that connects your intentions to the database's actions. The heart of SQL is the query. A query is a command you write in SQL that asks the database to retrieve specific information. It's like being able to ask very precise questions and get instant, accurate answers. For example, a sales manager might want to know, which customer spent more than $500 with us last year? Or, what are our top 5 best-selling products in the state of Texas? Instead of manually sifting through stacks of paper or giant spreadsheets, they can write a SQL query to get that information in seconds. This is what we call an ad hoc query, a question you think of on the spot. A basic SQL query has a simple, readable structure. The most common command is select. You use select to specify the columns or fields you want to see, from to name the table you want to get them from, and where to filter the results based on a condition. For instance, to find the names and prices of all products that cost more than $50, the query would look something like this. Select product name, price from products. Where price or 50. It's almost like writing a sentence in English, which makes SQL relatively easy to learn for beginners. But SQL isn't just for asking questions. It's a complete language for managing the entire database. It allows us to create new tables, insert new data, update that data, and delete it. It's the tool we use for both database development and maintenance. The commands are broken down into different categories based on what they do. A common misconception is that SQL is only for retrieving data. In reality, it handles the full life cycle of data management, from the birth of a table to the deletion of a record. It's really the one language to rule them all in the database world. SQL commands are powerful, and they can be divided into two main groups based on their purpose: Data Definition Language, or DDL, and Data Manipulation Language, or DML. It's important to know the difference. DDL is all about structure, while DML is all about the data itself. Think of it this way. DDL is the architect that designs the house, and DML is the mover that puts furniture in, rearranges it, and takes it out. You need both to have a functioning home, and you need both DDL and DML to have a functioning database. Data definition language commands are used to define and manage the database's structure. These are the commands you use to build your database from the ground up. The main DDL commands are create, alter, and drop. You use create table to build a new table, specifying its name and all the columns or fields it will contain, along with their data types. For example, this SQL command builds a simple products table. Create table products. product ID int primary key, product name varchar 100, price decimal this 10, 2. This one command creates the entire table structure, ready to hold data. Once a table is created, you might need to change it. That's what alter table is for. Maybe you decide you need to add a new column to track the quantity in stock. You would use alter to modify the existing table structure without having to delete it and start over. Finally, if a table is no longer needed, you can completely remove it and all its data using the drop table command. DDL commands are very powerful because they change the fundamental blueprint of your database. A common mistake is thinking you can undo a drop table command easily. In most systems, once it's gone for good. On the other side, we have data manipulation language, or DML. These commands are used to manage the data within the tables. They don't change the structure of the tables, just the records inside them. The core DML commands are insert, update, and delete. You use insert into to add a new record to a table. To add our volcano kit, we'd write insert into products, product ID, product name, price, values, 101, volcano making kit, 19.99. To change its price later, you'd use update products. Set price are 21.99, where product ID, cheese 101. And if you stop selling it, you'd use delete from products, where product ID, chi 101. These are the commands used every day to keep the database's information current. As we've journeyed from tiny fields to powerful SQL queries, we've seen how databases bring order to the world of information. But along the way, there are a few common misunderstandings that can trip people up. One of the biggest is confusing the hierarchy. Remember the building blocks. Fields are single pieces of info. Records are collections of fields about one item, tables are collections of records, and a database is a collection of related tables. Thinking a database is just one giant table or that a field is the same as a record will lead to confusion in designing and using them. Another key point to get right is the role of the DBMS. The database management system is not the database itself. The database is the collection of data. The DBMS is the software that manages it. It's the traffic cop, the security guard, and the helpful librarian all in one. It's what lets multiple users access data safely and consistently. A common misconception is that when you write a SQL query, you are talking directly to the data files. In reality, you are always making a polite request to the DBMS, which then figures out the best way to get the information for you. Entity relationship models and keys are another area where mix-ups happen. The primary key must be absolutely unique for every record in a table, no exceptions. And a foreign key is simply a primary key from another table used to create a link. People often struggle with many-to-many relationships. Just remember the rule. You can't connect them directly. You must always create a third linking table in the middle that has a one-to-many relationship with each of the original tables. This is a fundamental pattern in relational database design that solves a very common problem. Finally, let's not confuse a database with a data warehouse. A database is for running the business day-to-day operations, while a data warehouse is for analyzing the business over time, analytics. They are both valuable, but they are optimized for very different tasks. Mastering these concepts, from the simple field to the complex query, is the key to unlocking the true power of data. Data is one of the most valuable assets of any modern organization, and understanding how to store, manage, and question it is a science skill that is more important today than ever before.